Number 3. Sketch the graph of the following piecewise function. Be sure to indicate arrows, closed circle endpoints, and open circle endpoints. Alright, in this situation we have another one like number 1. Of course, the obvious difference is this one has 3 pieces, whereas the first one had 2 only. First, I take a look at the different pieces and I ask myself, what kind of a function would this be if f of x equals 4? Well, what that's saying is, no matter what you put in for x, the function's value will be 4, which leads me to the conclusion I have a function which is a horizontal line, where all the y coordinates are 4, no matter what x is. In the second piece, I see that I have a quadratic term. That is, I have a function which would be a parabola when graphed. And also, what I notice immediately is that it's positive, which means whatever piece I have, it will open up, as opposed to number 1, which was reflected. And finally, I have an x term which is to the first power. And right away, I conclude or recognize that as a linear equation. Whereas in the number 1, we had a positive slope. This negative or minus in front of x would give me a negative slope, which means it slants left. So in investigating my 3 different equations, I have a feel for what the parts should look like. Now I have to determine exactly where they start and where they stop. And of course, that is based on the description of the domain. So for my first piece, I have my first table where I start with -2. Because it's less than -2, I have to remember that -2 is not included. If it had been less than or equal to, it would be included. I have nothing to mark. But I like to mark my table so that I don't forget when I graph with a circle around the open point. And now I continue on and I put in some values. It doesn't matter what the values are as long as they're less than -2. For my second table, I have a very interesting domain. My domain is the set of values between 3 and -2. This particular inequality has an equal to part, so that means I include the -2. But this one is simply less than, which means I exclude the 3. So I'm going to start with a smaller value of -2. And then I will increase, but I will not circle it, excuse me. I will increase it because it is included. Whereas I list some more values up to 3 and I will stop there. And when I stop there, this is a less than or equal to, so I will use my technique of circling the open point. And then of course I have an additional piece, and I know that's linear, and the domain is not only between 3 and 7, but also it includes 3 and includes 7. So I don't have to worry about any open points in my table, and I have just listed them from 3 to 7 for my domain. Now remember, we're getting the y values by simply using the rule, and the rules are located above each table. Okay, now let's take a look at our graph. For the first piece, that was simply, I started graphing at -2, 4. That was the first point in the table, but it was open. It was not included. And all y values were 4, and the last value, there's no last value because it goes on continuously. So you notice I put an arrow here. I'm now looking at the middle piece. And in the middle piece, I am inputting my values in the rule and graphing them from the table. And I graph every point as I see it. I know it's a parabola, so I know its basic shape. So when I connect the dots, I should see somewhat of a curved graph. And the open point was the last point, 3, 6. So I remember because I looked at my table and it was circled. And then the very last piece, which was the linear piece, and it's slanted left because there was a negative in front of x, remember? In this piece, I have endpoints, they're both included, and I simply have a line segment.